Hi. The extremal types theorem says that if the limit exists, then it can take three different forms. The Gumbel limit, or type 1, the Fresher limit, or type 2, or the Weibel limit, the type 3. Now the question is, can the three limits, can they be combined into one mathematical formula? The reason I'm asking is, all right, I will explain why we need, why it is convenient to combine the three limits into one. So let me write something. So the question is this, that because at the moment you currently have three possible limits, but for somebody who's not a mathematician or a statistician, like say for example somebody working in agriculture or biological area or finance or business, they may not know, they may not have the mathematical ability to check the conditions 1 to 3 to see which of the limits is attained. So for that reason, it is convenient to have one mathematical formula, a single mathematical formula, right, that combines the three limits, that is the Gumbel, the Fresher, and the Weibel, into one formula. And this can be done. This can be done. So the combined formula The combined formula is known as the generalized extreme value distribution, or GEV distribution, right? So the GEV distribution combines the three limits, the Gumbel, the Frechet, and the Weibel, into one mathematical formula. Okay. So now let me in the next pages of this video I will explain what a GEV distribution is. So a random variable is said to follow the GEV distribution if its CDF is given by the following formula. Right? Where this is the support of the CDF, and there are three parameters: the psi parameter, the mu parameter, and the sigma parameter. So the psi parameter can take any value between minus and plus infinity, and is known as the shape. It's known as the shape parameter. The sigma parameter must be positive and is known as the scale parameter. And the mu parameter can take any value and is known as the location parameter. Right, so the three parameters control respectively the shape, the scale, and the location of the GEV distribution. Now the notation I shall use to denote a GEV random variable is the following. This is the note. So if I write down GEV in brackets mu, comma, sigma, comma, psi, that means that the variable x follows the GEV distribution with these parameters. Now the next thing I like to talk about is the domain of x. Now I told you just on this line that the domain is given by this inequality, but to be specific, let me be more specific. So domain domain is the same as support, right? Support of x. Now let's consider the case where the parameter psi is negative, right? In this case, the support or the domain is, as I said in the previous slide, is given by this inequality, right? And this, because this is a negative parameter, when you change the terms around, this will be the same as saying that, all right, let me do it one at a time, okay? So this is the same as saying that greater than -1. Now if you divide both sides by psi, you get x minus mu divided by sigma, and the sign will change to less than. Okay, so this is the same as saying that x is less than mu. Okay, so the domain is the interval from -infinity to, right? Now next, let's consider the case where the parameter psi is equal to 0. So in this case, this inequality will become because this is 0, this will become 1, right? And 1 is always greater than 0. So hence, so what this means is that the domain is all the numbers on the real line. So since this is true for all x, the domain must be all the numbers on the real line, right? And next, the third case to consider is where psi is positive, right? So in this case, the inequality is the same as this, and this is the same as this, because psi is a positive number. When you divide, you do not need to change the sign. So this is the same as all right. So hence, in this case, the domain is so in this case, the domain is all the numbers from mu minus sigma by psi to plus infinity. So just to summarize, let me write down so the domain the domain of x, right, is equal to Right, so this is a summary of the support or the domain of the GEV distribution, depending on the sign of the shape parameter. So if the shape parameter is positive, then the domain is from mu minus sigma by psi to plus infinity. If the shape parameter is 0, then the domain or the support is from minus to plus infinity. And if the shape parameter is negative, then the support is from minus infinity to mu minus sigma by psi. Right. At the beginning of this video, I mentioned that the GEV distribution includes the three limiting distributions, the Gumbel, the Frechet, and the Weibel, as one formula. But I did not explain why that is the case. So that's what I'm going to do now. So the question is the following: how So the question is, how come the GEV combines the three limiting distributions, namely the Gumbel, Frechet, and Weibel, into one formula? So let's start with the case that psi is less than 0, right? Right. In this case, the CD of g of x, which, as I already mentioned, is equal to this. Now this one you can write as follows. Right? And furthermore, you can write this as follows. Right. Now, let me use a red pen. you should look at this guy here. Let's call this B. If you look at this guy here, let's call it A, right? And clearly, because we are assuming that psi is a negative number, A is a positive real number, right? And B can be anything. B can be any real number, right? So what I'm saying is that this one you can write as exponential right. Now furthermore, let me call this is equal to alpha. Now once again, because psi is a negative number, alpha is positive, right? That's because psi is negative, right? So what you have is the following, that this is exponential right, and this is the, if you recall what same type means. I talked about same type some time ago in a previous video. Now what you have here is of the same type as same type as this. That's because A is positive, B is any real number, and alpha is also positive, right? So what we have shown is that the Weibel limit in the extremal types theorem So we have shown that the Weibel limit is a particular case of the GEV distribution when the parameter psi is less than 0. The next case I'm going to consider is where the parameter psi is positive. So in this case, the GEV CDF can be written as follows. Oh. One minus right. All right, now let me call this guy here equal to B, and let me call this guy here equal to A, and let me call this guy here equal to alpha. Now we can see, given the fact that psi is positive, A must be a positive real number, alpha must be a positive real number, and B can be any real number. Okay, so hence we can write the above as okay, and this is of the same type as right. And you may recall that what you have here is the Frechet distribution, right? So the conclusion here is that the Frechet limit right. So we have shown that when the shape parameter is positive, the GEV contains the Frechet distribution, the Frechet limiting distribution, as a special case. So the next case I'm going to consider is where psi, the shape parameter, is equal to 0. Next we consider the case psi equal to 0. In this case, the CDF of the GEV distribution, which is this, you cannot put psi equal to 0 directly into this formula. What you need to do is to take the limit as psi approaches 0. So you can write this. As the limit as psi approaches 0 of exponential Now I'm going to write this term here as follows. Right? Okay, now I'm going to make a substitution. I'm going to set m equal to 1 divided by psi. Okay, so under this substitution, this limit will become the limit the limit as m goes to infinity, because if psi goes to 0, then m will go to infinity. So this will be exponential in brackets right. Okay guys, so in the next step I'm gonna write the limit as this, right? And in the following step, I'm going to use a fact that you may recall this from courses that you have taken previously, that if you have something like 1 plus z divided by m power m, as m goes to infinity, then the limit of this is e of z. I think this is the result you may be familiar with. If you are not, please make sure that you are familiar with. Okay, so I'm going to use this result. So using this result, I will get the following. Okay, and this you can write as, there's no m here, so we can leave out the limit. There's no need to put the limit. So right now, this you can write as you can write like this, where your a is equal to 1 over sigma, which is a positive number because sigma is a positive number, and your b is equal to mu over sigma, which can take any real value. So hence what we have is that this distribution function is of the same type right, is of the same type as this, which is the CDF of the Gumbel distribution. So what we have shown that the Gumbel limit is so we have shown that the Gumbel limit is the particular case of the GEV distribution when psi is equal to 0. Right, so hence, to summarize, we have shown that the three limiting distributions, the Gumbel, the Frechet, and the Weibel, are particular cases of the GEV. In other words, the GEV contains the three limiting distributions as particular cases. Gumbel when psi is equal to 0, Weibel when psi is less than 0, and Frechet when psi is greater than 0. Okay. So just to summarize what we have done so far. And the Weibel limit and the Frechet limit Okay, so this summarizes our findings, as I said. Okay. In this slide, I'm going to talk about the density function, or the PDF, the probability density function of the GEV distribution. So I'm sure all of you know how to find the density from a CDF. All you have to do is to find the derivative. So g of little g of x, which will denote the PDF, is the derivative of the capital G of x, which denotes the CDF. And so we saw from earlier that the formula for the CDF is, this is the formula for the CDF. Alright, so we need to differentiate this with respect to x to get the ETF. And if you do that, this is what you will get. I'm sure all of you guys know how to do differentiation. So multiplied by Alright, so this is the density function of the GEV distribution. In this slide, I'm going to talk about the quantile function or quantile of GEV. Quantile function of the GEV distribution. Now, I don't know whether you know the term quantile. This is something you should have covered in your first year. Now, a quantile quantile, this is the term quantile. The notation is x subscript p. It's defined by this equation that the probability that the random variable is less than equal to x subscript p is equal to p. Alright? So this is the definition of a quantile, or the pth quantile, the notation x little subscript p. Now for the GEV distribution, you should call this, say, plus, for example, right? Okay, plus is equivalent to G at xp. Remember, G is the CDF of the GEV, being equal to P. Alright, so in other words, we know what G is. Okay, and now taking the logs both sides, this will reduce to the following. And taking the minus 1 to the right hand side and taking the power to minus psi, you will get right? And taking the 1 to the other side, you will get right? And finally, taking everything here to the right hand side, you will get the formula for xp as follows. So mu plus right. So this formula here, let me use the red color here, this formula is known as the pth quantile of the GEV. Okay, so in particular, you should put p equal to half. You should put p equal to half, then you get the median. So in particular, x half, right, which is the median of the GEV, right, is given by the following formula: mu plus sigma over psi right. Okay guys, right. In this slide, I'm going to talk about return level of the GEV distribution. Now I need to define what a return level. A return level with period t is in the units of years. So this is capital T, guys, is the level right? So it's the level that is expected to be exceeded on average once in every t years, right? So the notation I shall use now is little x subscript t denote right. Let this denote the return level with period t. Remember, t is in years. Now, because of the definition, we must have the probability that the random variable, in other words, a GEV random variable, say x, greater than little x of t, right, must be equal to 1 divided by t. Let me explain why this is the case, because you should go back to the picture. You should go back to this picture that I showed you a while ago. This is the definition 1. This is where the GEV distribution comes in, right? And you see that this is a 1 year period. And over this 1 year period, there's only one extreme value, right, which is this one. And you should have t years. Instead of 1 year, you should have capital T years. You will have capital T extreme values, right? So the probability that something is exceeded over a capital T year period, right, is 1 over t, right? Because you have capital T extreme values over capital T year period. So the probability that a GEV random variable is exceeded once in every t years, right, is 1 divided by t, because it's one out of capital T, because there are only capital T extreme values over a t year period, right? So this follows from the definition of return level, right? So this is the same as saying that the probability that x is less than or equal to xt is 1 minus 1 over t, right? Okay, so and this, you can solve this. Now you can put your g here. G at xt must be 1 minus 1 over t. G is the CDF of the GEV, as you know. Then you can put the CDF of the GEV, which all of you know is exponential. Right, now if you solve this equation which is similar to what I did in the previous slide, so you should solve this equation for xt. This is what you will get. I'm not going to go through the details, but I'm sure you will know how to do it. So this is what you will get. So this is the formula. So this here is the formula for the return level with period t. Okay. Now in this slide I'm going to talk about estimation. So this is, remember that it's not worth having a distribution unless it can be estimated. So I'm going to show you how to estimate the parameters of the GEV distribution using the method of maximum likelihood. I'm sure you learned MLE, or method of maximum likelihood, in your second year. If you haven't learned it, then you can look at the course notes for the second year course, which may be online. Alright, so suppose you have a random sample from a GEV distribution with parameters mu, sigma, and psi, and we want to estimate these three parameters, and for that we want to use the method of maximum likelihood. So once again, if you haven't learned of this method, please make sure that you learn about it as soon as you can. Right? All right. According to this method, the first thing you need to do is to write down the likelihood function. So that's what I'm going to do. The likelihood function of the three parameters mu, sigma, and psi is as follows. Remember, it is defined as the product of the density function of the GEV from I from 1 to n. Now we know what the density is. We worked it out just a few minutes ago. So the density is Alright, so this is a product of the density of the GEV distribution. Now you should simplify this. This is what you will get. You will get 1 multiplied by Alright, so this is the simplified form of the likelihood function. And the next step to do in maximum likelihood method is to take the log of the likelihood. So that's what I'm going to do now. So the log likelihood function is the log of the likelihood which is going to be this. Right. Right. So this is the log likelihood. Now the maximum likelihood estimates of the 3 parameters are the solutions of the equations that we obtain after differentiating the log likelihood with respect to the 3 parameters. So let me write that down. So the MLEs of mu, sigma and psi are the simultaneous solutions of these 3 equations. So the partial derivative of the log likelihood with respect to mu, the partial derivative of the log likelihood with respect to sigma, and the partial derivative of the log likelihood with respect to psi. So you set each of these to 0 and solve them. So the simultaneous solutions of these equations will be the MLEs of mu, sigma and psi. Now I'm sure you guys know how to do the differentiation. these are the three partial derivatives. So the first equation, this one here, is the partial derivative with respect to mu. This is the partial derivative with respect to sigma, and this is the partial derivative with respect to psi. So let me call this equation 1, call this equation 2, and call this equation 3. So the MLEs of mu sigma and psi are the solutions or the simultaneous solutions of equations 1, 2, and 3. And these equations are not easy to solve. And you cannot solve them analytically. So they have to be solved using some computer programming package. Fortunately, there is a package, or there is a command called GEV. In the R language, I'm sure most of you know the R software. So this command, FGEV command, in the R software can compute the MLEs of mu, sigma, and psi.